synthetic. It is a vast field from molecular level to. So Phillips G, actually we in India we tell G actually to give respect. So I tell the student. So Dr. Phillips, so he is competent, and I think he is very much a good teacher. So in this seminar come interaction, all we can enjoy. And I especially tell the students, it is a really privilege for you. After his talk, all try to, not all, few search topic discussion, or is few, especially teachers and students. Thank you.
Head of the department.
It is a great honor for me to introduce Dr. Philip Fantuzzi. He is a lecturer in chemistry at the University of Kent. Dr. Philip Fantuzzi to deliver his lecture.
Thank you, teacher. One thing, thank you.
Okay, good afternoon, everyone. I hope you all can hear me. Yes, first of all, I'd like to thank very, very much everyone here for being here, for receiving me so warmly. I'm very, very happy to be here so warmly. I'm very, very happy to be here. Special thanks to Aritro, to Cosmic Chemistry, Computational Perspectives on Molecular Structure and Function. And this place here, I'm from the University of Kent. These are the White Cliffs of Dover. This is like only the university, but some beautiful parts of the computational chemistry. What that is, discussing that the following way. So what is computational chemistry? Before that, we have to understand that that are combined with the fundamental laws of chemical physics in order to study processes that are relevant for chemistry. And if we define theoretical chemistry like the probe as a way to probe the molecules. So that is the main definition here. And the focus then is on obtaining results that are relevant to chemical problems. Which problems? In principle, anything. So the limit is your imagination. Another way that I like to portray computational chemistry is that way. Is showing these nice figures here. So on the left, we have an archipelagos. We have here the Andaman Islands here in India. And what I like to portray, and you guys to imagine, is that all the experimentally known world is everything you can see here. Okay? So the islands and everything that is above the water, the sea level, is what you can know or you can probe experimentally. So this is all the known chemistry. And you can understand a lot about nature, about the universe, about molecules, about any chemical related system by investigating the topology of these islands, by investigating everything that is above here. For instance, how these islands connect, how the landscape is originated from the different parts here. However, we all know that underneath this water, there is a lot hidden, and a lot of that is not accessible through experiments. So in order to better capture all these effects that are here, it's very important to go underneath this water. And with computational chemistry, we can reach these parts that are not accessible through experiments. So in that perspective, computational chemists are divers, okay? And what is also very interesting about that is that we have different methods, different levels of theory to probe molecules and systems, and they have different accuracies and different possibilities. So in the end, what you have is that if you have a very, very powerful approach, it will work very well if you are working on experimentally unknown waters, or if you are working here in the experimentally known world. So if the method is good, it will be equally good here and there. But if the method is bad, it will work terribly here and terribly bad here as well. So it's very important to understand how the methods work, what are their limitations, in order to understand the whole topology of these systems. So this way is how I usually like to start, by portraying what computational chemistry is. Okay, and then we have, what I do in terms of research, I usually say I have 3 different research areas. The first one is to investigate the very small, why the foundations of chemistry, why when atoms are brought together, you form a molecule. So the chemical bond theory, the nature of the chemical bond. So investigating the very small. The second area is to investigate the very large, which is how molecules are formed in space, how molecules are formed in interstellar medium, and how the formation of these organic molecules is associated with the origins of life. So this is the second topic. And the third topic, finally, is functional molecules, is how can you use these sets of theoretical frameworks to then investigate molecules that have potential applications in different areas like bioactive systems, optoelectronic devices, energy applications. So these are the 3 areas. And I will briefly touch on these 3 areas just to give this perspective of the powerfulness of these methods in order to investigate chemistry. And I will start by the first one, which is from chemical bonds. So the nature of the chemical bond, okay? And then I will start with our dogmas of the chemical bond, okay? So these are things that we study since year 1 in chemistry, and I will briefly touch on them because it's very interesting. So the first dogma that we have is that a chemical bond is formed when atoms share a pair of electrons, okay? So for instance, we have the Lewis model and the idea that if you have this electron pair formation, you form a chemical bond, okay? That's the first dogma. The second dogma of the chemical bond is it's not all electron pair that is going to make a chemical bond. They need to have the appropriate spins. You need to have one spin alpha and one spin beta, then you form a singlet coupled pair that then you can form a chemical bond. If there are 2 alpha spins, you are not going to form a chemical bond. So the second dogma is that the electron spin is directly involved in the formation of a chemical bond. So if you have 2 hydrogen atoms, you can form a molecule if these atoms have different spins, but you will form a dissociative state if they are alpha spins, if the system is a triplet, okay? So that's the second dogma. And the third dogma is that it comes from the Virio theorem, and it says that the chemical bonds, they will result from a reduction of the total potential energy of the system. So if you separate the total energy of H2 here into the potential and the kinetic part, you will see that the potential part is going down here, and then the well, the potential well here is formed by the potential term of this separation. And this comes because of the Virio theorem. Okay, so these are the 3 dogmas of the chemical bond. And now that we discussed about them, let's break them. Let's break the dogmas. So let's deconstruct them. So the first dogma, a chemical bond is formed when atoms share a pair of electrons. However, if you get the simplest molecule, this is not obeyed. The simplest molecule we have is H2+. Well, H2+ is a bonded system. You have a very strong chemical bond here, but H2+ has only 1 electron. So a chemical bond is something more fundamental than a share of a pair of electrons, okay? And if you have only 1 electron and you still have a chemical bond, or you have a potential well here, the electron spin is irrelevant, okay? It has only 1, so it's not any electron pair with different spins. So the first 2 dogmas are easily broken if you just consider the simplest molecule that exists, H2+, okay? And now let's break the third dogma. The third dogma, again, is that this is associated with a reduction of the total potential energy. Okay, so, but we know that if you bring the atoms together, we know that the chemical bonds, they will result in an increase of electronic density in the internuclear region, okay? And if you are doing an increase of electronic density there, when the atoms are brought together, you have an increase of electron density in the center, so the electron repulsion will increase because now this density is confined in a smaller volume. Okay, so this term increases. The nuclear potential, the repulsion here, will also increase because the nuclei are closer, right? And they are less. The electrons are not. There's a strong effect here that the nuclei will feel the presence of the other nuclei better if the electrons are moved towards the internuclear region. So this will also increase. So what happens with the electronucleus term? The electronucleus term, when you do this type of change from the atomic world, where the electron density is associated with the atom, and now the electron density is associated with the molecule, you are also displacing electron density from the atomic region to the bonding region. So you are working against the electron nucleus potential interaction, the attraction here, because you are putting the electrons farther away from the nuclei, which means that these terms also increases. So if these three terms increase, the bond formation cannot be associated with a potential energy reduction because the three terms increase. So because of this reasoning, we can say that the third dogma is also false. It's also wrong. The Vireo theorem cannot be used to explain chemical bond formation. Okay, so what do we have in place of all of that? Then I will bring a bit of physics and I will talk a bit, very lightly, about the double slit experiment. Perhaps you already saw that. The idea here of the double slit experiment is that you have a detector of electron here, you have an electron source here, and you have two slits, okay? Then let's close slit 2 and let's just leave slit 1 open and see what is the pattern of detection of the electron that is coming through the slit. It will be described by this curve here, which by definition is the square of the amplitude, of the wave function amplitude here, okay? Of this event, of the passing through the slit 1. If we do the same with slit 2, we close slit 1, we open slit 2, and we measure the electron density, we will see the curve here in blue, with a maximum here exactly at the center, and a distribution like this Gaussian here, that can be obtained by the square of the wave function of this second event here, okay? So what happens if you leave the two slits open? Well, classically, you would expect something like this, just the sum of the two amplitudes, or the sum of the two probabilities in this case. However, if you then measure, what you see is this, okay? It's a complete different pattern that appears experimentally. But what is more weird about that is that you can obtain this pattern considering the wave functions of these two different events here, but instead of just summing them like that, you actually square the sum of the amplitudes. If you do like that, and you open the terms, you will have the same terms that appear here before, but you have another term here, which is an overlap between the two wave functions. And because of this term, which is the interference term, now you can describe the electron distribution here in this experiment. But this reveals something more fundamental about quantum mechanics, which is the Feynman's second rule, which is the idea is that when an event can occur in several indistinguishable ways, the probability amplitude of the event will be the sum of the probability amplitudes for each way considered separately. Which means, instead of summing the squares, you square the sum, and then the term appears. Nice. But what does this have to do with the chemical bond? Everything. We can plot here Feynman diagrams of the H2 molecule. Feynman diagram is how the electron interacts with the proton in a molecule through time. Okay? So we can say that this electron is navigating through time, interacting with this proton, this other electron here with that proton, and we can define that this amplitude of this event is given by the product of these two events separately. But the electrons are indistinguishable. When you measure the electron here, you don't know if this electron is exactly the one that started there, or if it's the electron that started there. So you can have a second diagram where you actually interchange the positions of the electrons. Okay? And then if you have that, you have this other wave function here. And as we know from the previous slide, the total probability will be defined by the sum of these two taken to the square, and then it will appear an interference term that now if you use orbitals to define that, you get that your wave function has this shape here. And long story short, this is a valence bond type wave function that appeared naturally by just defining the densities, the space-time diagrams. And what comes out of that is that if you see the probability, there is this term here that is the classical term and the interference term. And if you now from there you get the energy, you see that the energy is only associated with the formation of the bond is only negative if this interference term is appears, which means that in the absence of the interference there is no chemical bond. Okay? So the chemical bond is not the share of electrons. It's a consequence of quantum interference. And not that long ago, there was a method to describe the interference energy and the interference property for polyatomic molecules. So this idea of interference is known since the 60s, but no method was able to capture the interference contribution of different bonds in a system with more than one chemical bond. So this now is possible, and the basic idea is that you can separate the total energy of the system into a part that is classical, like the probability terms from before, and a part that is associated with the interference of these orbitals. And if you do that, and now you get the H2 molecule, for example, you see that the formation of the potential energy well here is completely dictated by the interference energy term. Okay? And if you plot the electron density associated with that interference, you see that here the regions in red are regions where the electron density is being removed, and here in blue is to where this electron density is going to. And then you see that this dictates exactly the formation, the concentration of electron density in the middle of the atoms. So the interference effect is being captured here by this model. Okay? So this is a very interesting approach to investigate chemical bonds, and we are doing that a lot. So this is the first area that I mentioned. There's a lot of molecules that we are investigating. The idea is to go systematically investigating different classes of bonds, different types of bonds as well, metallic bonds, ionic bonds, covalent bonds, charge shift bonds, all of these types of different bonds, and see what happens from the fundamental point of view, what is the effect of interference. I will not discuss all of these cases, I will discuss just one, because I think this is a very interesting and relevant system, which is benzene. Okay? Well, benzene, we also study and investigate a lot what is the origin of the structure of benzene. So we know that benzene is flat. We know that benzene has a D6H symmetry, so it's a perfect hexagonal structure. And this is attributed to the pi electrons, right? You have the pi cloud, and this is then what causes the molecule to contain these properties. However, it's very important to also highlight that even this knowledge that we usually know for ages, there's still some debate about this. And one very interesting example and comparison is if you get other molecules that have the hexagonal structure and how they behave with the distortion, like the distortion for the Kekulé mode, where you concentrate 3 bonds. Okay? So let's get H6, for example. H6, if you are in the hexagonal structure, and now you make the distortion for the 3 bonds, you will form 3 hydrogen-hydrogen bonds, which are quite strong. Therefore, you anticipate that the system will prefer to form these 3 bonds and will prefer to distort to a D3H structure. So H6 will be more or less like that. A transition state, a maximum here in the hexagonal structure, and in the distorted one will be a minimum because it will form these 3 hydrogen-hydrogen bonds. Okay? Now let's get lithium-6. Very weak. So there is no thermodynamic gain in distorting the molecule to a D3H structure because this bond is very weak. So you expect lithium-6 to be something like that. The minimum will be in the delocalized, in the perfectly symmetrical structure, and when you distort, you increase the energy. Okay? Now let's go back to benzene. If you have benzene, and now you distort in these Kekulé modes, you are going to form 3 carbon-carbon double bonds, which are strong. So you can imagine that actually the pi electrons would prefer to distort, because then you will form a more stronger bond, these 3 two-center, 2-electron bonds. But we know that actually the benzene behaves like that, right? So there are some groups and some ideas that actually the structure of benzene doesn't come from the pi electrons. It comes from the sigma electrons, because if you stay them in the perfect symmetrical structure, you don't have any, you maximize all the sigma interactions there. And this is, and the distortion, the preference of the pi electrons to distort is called pi distortivity. So we entered in this arena trying to use this interference method to investigate that, and what we saw was more or less like that. If you have the perfectly symmetrical structure, you actually are forming a 6-center, 6-electron pi bond. So it's one bond of 6 centers and 6 electrons. But when you distort that, you form 3 strong 2-center, 2-electron bonds. So from the pi perspective, it's better to be here distorted. If you get the energies, you can see that from the interference energy, you prefer to distort, but there is another effect that is bringing the system to a symmetrical case, okay? And, but what we saw is that this is not associated with quantum interference. So in principle, the structure remains the symmetry, not because of bonding, but because of classical effects, basically associated with the kinetic energy of the electrons. So you see this, that we usually consider that is already fixed and solved. There's still a lot to debate. And this is what I wanted to bring in this case. So with that, I finished part 1, and I will start part 2, which is the functional molecules that I mentioned, okay? And about these functional molecules, there is a particular element that usually is incorporated into molecules and makes very drastic changes in the reactivity patterns. And this element is boron. So there is a lot of boron-based compounds that are known, and usually boron, when incorporated to an organic molecule, brings a complete set of new reactivity. And one of the main reasons why boron is so interested in that is because boron has only 3 valence electrons. Therefore, it's far away from obtaining the octet, right? And then it becomes very reactive. It's a very good pi acidic system. So it's a very good P acceptor, and therefore it makes, when it incorporates that in molecules, it usually makes it very reactive, okay? So there's a variety of boron-based compounds, and recently we were able to use ligands to stabilize boron in a very peculiar structure. So for instance, we know diboranes, which are analogous to alkanes, but are weird because usually there's a delocalized hydrogen atom around. We know now diborenes, which are analogous to alkenes, so you have a boron-boron double bond. And you can also have diborines, which will have a boron-boron triple bond. And just imagine, the element has 3 electrons, and you are using ligands to force these 3 valence electrons to bind to another atom with 3 valence electrons in a triply bond system. This, until recently, was considered a chemical sin. It's impossible to make it, but now we know how to make it. And these molecules are fascinating from the experimental point of view for various applications. So applications of these systems, for instance, optoelectronic, semiconductor industries, for small molecule activation as well is very relevant, for homogeneous catalysis, for medicinal chemistry. There's a plethora of applications here. And then I will show some examples of these applications. One is when you incorporate that into acenes. Acenes are these molecules like polycyclic aromatic hydrocarbons that are linear like that, okay? And then one thing is very interesting, if you start to put lots of benzene rings like that in a line, at some point the system will become so reactive that it becomes a biradical. And then if it becomes a biradical, you reduce the homo-lumo gap there, and then the molecule becomes more reactive and more prone to semiconductor. However, if you incorporate boron, basically, long story short, what you can do is you can reduce the number of rings that you need to have in order to have this effect. Okay? So what we saw in this work is that if you use, first, that you can synthesize a boron analog of the anthracene molecule using one of these ligands. This is the CAC ligand. CAC ligand is here. This is a Lewis base. Remember that boron is a Lewis acid, right? And then with that type of chemistry, you can generate the analogous of this. And look, only with 3 rings, you can already have a system that behaves as a biradical. So not only that, but these biradical you can stabilize, you can get a crystal out of that. And it's very reactive towards like small molecules. It can react with CO2, it can react with CO, it can react with N2. Okay, N2 is very unreactive. Some of these molecules, they are reactive towards the N2 as well. So it's a very interesting system to obtain. So we did a lot of calculations. This is a type of molecule you can obtain when you react that with CO. And this is an example of the computations helping to understand what's going on with the molecule, okay, that was synthesized. Another example here is in catalysis. And there is a dehydroboration reaction, which is very important, where you incorporate a boron into, in this case, into an imino group. Okay? So the reaction looks like that. However, you need a catalyst for that. If you just try to react two like that, it's not going to work. And one catalyst that we discovered was the this dibora-anthracene system again. But in this case, it doesn't have these ligands to stabilize. So actually, this is a dianion. So you see here there are 2 lithium plus atoms here as well. And what we discovered, long story short, is that this molecule is indeed a catalyst. But it's a very weird catalyst, because what happens is that in the first few cycles, you are indeed catalyzing that reaction. But after some cycles of reaction, you are generating BH3. And BH3 takes the role of the dibora-anthracene as a catalyst of the reaction. Okay? And this we saw from the computations. And then we came back to the experimentalists. I'm sorry, guys, but the molecules you synthesized, they are not the true catalyst. Of course, they were not happy when we told that, right? However, they crafted another system, putting now like a bond here between the boron atoms. And though in that case, indeed, from the calculations, we saw that this is indeed a true catalyst. It's not generating BH3, it's just acting as a true catalyst. And how to do all these experiments, it's a hard work. It was done by Christoph Herock in Germany. He was my PhD student while I was there before moving to Kent. And you see that there's a lot of calculations you have to take in consideration, solvent effects, you have to take into consideration the counter-cation. Remember that I mentioned that this is a dianionic species. So there's a lot of effects at play, so it's quite complex. And but yeah, and another thing that we saw is that it's also very important to consider these effects, the solvents, the counter-cations. And one example is here, because here is the reaction mechanism for this reaction. And what we saw is that this first barrier here, which is the rate limiting step, if you consider the bare dianionic case and try to investigate that, this barrier is around 45 kilocalories per mole. So something was wrong. And then we said, oh, perhaps it's because we need the counter-cations. And then the barrier fell to 37. So it's still very large. So perhaps we need to consider also the solvent. And then after considering the solvent, this barrier was decreasing until we got a barrier value that is suitable for the experimental conditions. So that indeed now we can understand, and we can also highlight the importance of considering all these effects that might be happening in the chemical reaction as well. They might be important to model together with your reaction. Okay? So that is the outcome from this and the message behind this work. But you can have some other stuff that are very interesting. That reaction was happening in the ground state. So we didn't use light to go to an excited state to make the reaction. But sometimes you need to. And then there's this other reaction which is fascinating, because see what's going on here. You have the diboroanthracene, and you are making a photoisomerization. You are making another type of polycyclic aromatic system, but now you have this 5-membered ring here, and you have this 1, 2, 3, 4, 5, 6-membered ring here. Okay? And you can only make this reaction with light. And then we wanted to investigate what's going on. And in the ground state, in the ground state, indeed what happens is that, you see, all steps are okay for the reaction to happen, with exception of the first one. The first barrier here is 62 kilocalories per mole. This is basically impossible to react in the ground state. However, if you excite the molecule to the excited state, and you go through this same step, you see that in the excited state, the molecule can react barrierlessly. Therefore, you indeed need the radiation, and then when you do that the proper way, you can go take the molecule to the excited state. The molecule will win this first barrier, it will decay back to the ground state, and then everything else can happen easily. So an example of that, not only ground state reactivity is relevant, but sometimes you also need to consider excited state reactions. Okay? Great. So we are almost done with the main group part. There's also another example of these collaborations between experiments and theory. This is very important. So our experimental partners, colleagues, they came with this fascinating molecule here, which has a naphthalene core and this diborite ring here, so carbon-carbon, boron-boron there. And they came with the idea that, oh, okay, you have a double bond here, then you have an anti-aromatic diborite system, stabilized by these guys. Okay, fantastic. So everything looks nice. Please do some calculations to support our hypothesis. There's only one thing that is weird. We say that this is a double bond, but actually from the crystal structure, our crystals, the bond is too elongated. And then, okay, let's see. And then we did a lot of different calculations, and what we realized was the following. This bond is indeed very long, so it's not a double bond. So what's going on there is that you don't have a double bond, you have a biradical. Okay? And then we told them, guys, you have a biradical there. Therefore, all your NMR data is wrong. They were not happy with that comment. And then we told them, if it's a biradical, do EPR measurements, and there will be a signal there. And then they did, and the signal was there. And then they were happy again. Oh, okay, so now we understand what's going on. Thank you very much, guys. And then we just recrafted the paper, and instead of being the first anti-aromatic stabilized naphthalene stabilized diborite, it was the first biradicaloid diborite system. Okay? And with that, just another idea that is very important, this synergy between experiments and theory. Okay? I will skip this part here, just for the lack of time, but if you want, we can discuss after a couple of that. This is associated with the formation of very large rings, as well using boron, and what is the relevance of those to understand if you can form analogous of carbenes, but with boron, which are the borylenes, and if they can bind together to form a boron-boron double bond. But just let's skip that and go to the last example, which is a fascinating one, because these boron-based molecules, they are so reactive that some of them can indeed react with N2 from the air, and you make a system like that. Okay? So the N2 is activated. It's very difficult to do that without a catalyst in higher temperatures. This is ambient temperature. Not only that, but if you have a larger pressure of N2 in the system, you can make two N2 molecules react with each other, forming N4 between the boron atoms. Just imagine how crazy it is, because you can start making N2 not only reactive, but also react with another N2 molecule. This is a very weird chemistry that boron systems are being able to do. And another one that is very important is that not only you can activate nitrogen, but you can make it react with H2, and then you can lead to ammonia. And the N2 to ammonia conversion is very, very important from the industrial point of view, and it's very costly for us because it's a very costly reaction, okay? And then in this case, what we saw is that the system can do that, but it doesn't do that catalytically. In the last step, there is a problem, and you can only generate ammonium, not ammonia, and not catalytically, but stoichiometrically. And therefore, it's still not catalytic, the system. But we are almost there, we think. And then in this work, we were investigating if we can improve this N2 activation. So this is actually a partnership with Tazpur University here in India. And we basically investigated theoretically, and we are designing new ligands in order to improve the interaction with N2. So that is another thing that computational chemistry can do. Design new molecules for applications that are very needed in our society. And then finally, let's go to the last part of this talk, which is the cosmic chemistry, which is astrochemistry. So just some details about that. We know since the 30s, actually, now almost 100 years ago, that molecules can indeed be formed in space. Okay? We usually say the space is empty, very low pressure, very low temperature. No chemistry can happen there. But actually this is wrong. We have, even in those harsh environments, some chemistry. The first molecule detected was CH. Now we know more than 300 molecules, including ethanolamine, including complex organic molecules, fullerene, methylformate, acetic acid. We have sugars. All of these molecules were detected in space. Okay? And it's very important to understand how they are formed, because this can help us to understand what is the connection of that with the origins of life. Okay? So we've been doing in these last couple of years a lot of investigation on that. I will bring some examples of that. The first one is we wanted to investigate some of the saturated molecules that were already observed. So we have ethanolamine, propanol, some other molecules that we wanted to investigate what happens if you have the conditions of the harsh conditions of interstellar space there. And we wanted to investigate its fragmentation patterns. And from that, we used an interesting approach to measure these fragmentation patterns. And what we saw out of that is that we contabilized a lot of different molecular ions that were produced by these molecules that were already detected. Out of them, 25 were already observed by telescopes, by radio telescopes, but a lot of them were not yet observed. And then we came to the guys and said, yeah, please study these systems, because it might be that out of these are very relevant molecules you can detect there, because they can be formed by dissociation of molecules that were already detected. And so this work was recently published in Chemical Science, and these are some examples of these species that we observed from the theoretical point of view. They match very well the experimental data as well in terms of mass to charge formation, and then we propose these systems to be investigated observationally to try to detect. And particularly this one, the CH2NH2+, it's a very interesting system because it's very, very, very well formed by the dissociation of ethanolamine, which was detected in these environments. And we wanted to investigate this further, and this was done by a bachelor student in Colombia, Kelly Garcia Gonzalez, and she was investigating ethanolamine. Ethanolamine is relevant because it's present at the tip of these biomolecules. Okay, so it's a very interesting system, and we see that this molecule is formed more than 99% of the fragmentation pathways from ethanolamine will lead to that species. And this species was detected in Titan, but not yet detected in interstellar space. So we are suggesting, and we have a team of observational astrochemists trying to observe this molecule here as well. Another system that is very interesting, magnesium-bearing molecules. We know some molecules in space that contain magnesium, but we only know the ones that contain carbon atoms and even number of carbon atoms. So MgC4H, MgC6H, MgC8H, these ones we know. But the ones with even number of carbon atoms, they were not discovered yet. And then we were trying to investigate why. What are the peculiarities of these other systems? Long story short, what we saw is that instead of being linear, the most stable structures of these with even number of atoms, they are cyclic. So the rotational constants, all the spectroscopic properties, they will be completely different from what they were expecting experimentally, that would be something like a linear molecule as well. And therefore, if they want to try to measure these molecules, they should look for the cyclic ones and not for linear ones. And then this was the outcome of this work, highlighting also that computational chemistry can map the different possibilities of molecular structures and help guiding what are the preferred ones in different environments. And the last one, just to bring everything together, there's also the possibility of boron in space, okay? Boron is a peculiar element in this perspective because it's very rare in the universe. And the problem is that boron is not formed by normal nucleosynthesis in the stars. So usually the elements are formed by nucleosynthesis process in the interior of stars, but boron is not formed in this process. It's only formed when the star is destroyed, when the star explodes. So it's very rare. However, there's a very large body of literature highlighting that boron minerals are very important for the origins of life, because borate minerals can stabilize ribose and some other sugars in primitive oceans. Boron can also assist the peptide formation from amino acids forming the peptide bond. And even for an enantiomeric enrichment, it might be that boron played a role. So if boron is very important for life, we need to understand how the heck boron actually exists as molecules, okay? And how they reach a planetary system. Another PhD student, Cynthia Prieto Garcia, in this case she's from the University of Guanajuato in Mexico, that I co-supervise with them. She was investigating these linear carbon chains that are very abundant in the interstellar medium, and particularly comparing the cyano group, which is very abundant and very well observed, and replacing the CN by a BO, which is isoelectronic. And investigating that to see if these molecules could be potential carriers of boron in interstellar space. Long story short, what she discovered was that these molecules are indeed intrinsically stable. They are even more, the enthalpies, energies of formation are even more negative than the ones with the cyano analogs. They have larger dipole moment, which helps in the observation. So they look promising. They only have one problem. They are very reactive towards cyano and hydrides. Therefore, they might be formed, but they might be very fastly destroyed by these species from collisions in interstellar space. So we have this work. We want to expand the investigations of boron in space and in astrobiology as well. And this is highlighting the first attempt of investigating boron in space. Okay? So with that, we finally come to a conclusion of all this talk. And the main conclusion is that these quantum chemical methods, they provide key information into structure, stability, and electronic properties of functional molecules and astrochemically relevant species. And that in terms of the nature of the chemical bond, that quantum interference is responsible for the formation of them, and that the systematic investigation across distinct families of molecules is very well needed, because there's a lot of concepts that might change dramatically when we look them under the lens of interference. And the last conclusion, and perhaps my favorite one, is that boron is not boring at all. It's a very interesting element, and it should be studied more. Okay? With that, I would like to thank all students and collaborators that participated in these works that I highlighted. Special thanks to Aritro again for making this possible, that I'm here. And thank you very, very much once again to all of you for the warm welcome and for being here with me, sharing this moment together. Thank you very much, everyone.
Any questions, please? Please go forward. No problem. Nahi. You can ask.
Don't be shy.
Yes, please.
Sorry? H3 plus. H2 plus, yes. H2 plus exists, but H2 plus was not the first molecule formed in the universe. We already know what is the first molecule. There are some evidence from a lot of different experiments and modeling. It's the helium H plus molecule. That also exists, and that was the first molecule formed in space. And so these molecules are fascinating as well, very difficult to investigate experimentally. But with these tools, you can really investigate. And we recently published one about helium H+, showing that its chemical bond is a covalent bond. So helium is actually donating one electron to make a chemical bond with a hydrogen atom. Therefore, the oldest bond in the universe is covalent. Another interesting thing, H3+. H3+ is a very important astrochemical molecule. It also exists. It's a triangle. It's a perfect triangle molecule, and it only exists in interstellar space because the dissociation of one hydrogen atom, that energy of dissociation is larger than the energy of ionization of H2. So that energy of ionization is 13.6 eV, electron volts. It kind of buffers the energy available for other species in interstellar medium in general, and therefore because of this energy being higher than the buffer energy, it doesn't dissociate. So H3+ is there. It's making a lot of chemical reactions in interstellar space and playing a very important role in astrochemistry.
So which one is more stable, H2+ or H+?
Depends on how you define stability. I mean, if you're talking about thermodynamic stability, I mean, it's unfair to compare because you have one atom and it's a molecule. But H2+ is very, very, very stable. If you remember from that dissociation curve, there is a very large energy barrier to dissociate, and therefore it also plays some role in interstellar. But H3+ is even more important.
Thank you, sir.
Bonding, it says that two electrons are connected each other, generally.
Yeah.
That one electron comes and here is an electron and they combine and form a bond.
Yeah, that is the traditional view, right? You need two electrons to make the bond. But what we can show is that if you have H2+, you have one electron, it still forms a bond. So the bond is actually a consequence of the interference effect of not two electrons, but two one-electron states. So in H2+, you can say you have one state, which is the electron belonging to proton 1, and the other state is the electron belonging to proton 2. So you have two different one-electron states that are interfering, and that this interference phenomenon is responsible for the chemical bond formation. It's more fundamental than the pairing of electrons.
My question is, if there is a carbon radical is present, and hydrogen radical comes, then we say that CH bond is formed. But if only one electron comes towards it, we say that their carb anion is formed.
That's what, sorry?
Carbon radical present, and that accept one radical, means one electron, then we say that that is the carb anion. My question is, mainly the bonding is connected with the two electrons combined. So why here we says that it is the carbon anion? We can say that electron-electron bond is formed here.
Yeah, but notice that you can also form systems like a carbon-carbon or one electron bond, 2 centers, 1 electron bond. And a very recent example was when you have like a, I think it was a naphthalene core with some groups like that, and you have like 2 carbons nearby, and they managed to insert another electron there. And then the system became anionic, and they measured the crystal structure, and that those 2 carbons there in the anion, they did this. They came closer together. So that 1 electron was making like a bonding between these carbon atoms in the anionic state. So again, you can have bonds only with 1 electron. So H2 plus is definitely not an exception. There are a lot of systems which you have 1 electron chemical bond. Another example, for instance, alkaline metals. You can form lithium 2 plus, sodium 2 plus, and these systems are actually more stable than the neutral ones. Lithium 2 plus is more stable than lithium 2, and the bonding there is 1 electron.
Thank you, sir.
Any other questions?
Sir, how do you find these outer space molecules? We can't go there.
We cannot go there.
But how do you research about it?
Yes, we do that with usually with spectroscopy. Yeah. So we just point telescopes there and analyze the light that comes. If you are doing that with a radio telescope, you are getting rotational spectroscopy data. And the rotational data works as a fingerprint for the molecule. It's very, very precise, the rotational transitions, and you can use those rotational transitions to then say, we have this molecule there. In that particular point of the space we are observing, signals from that molecule are coming, therefore the molecule is there. And that is how we discovered most of the molecules. You can also use infrared for that. You can use then infrared telescopes. But as you know, infrared detects functional groups. So you can say, there's a carbonyl. There's a cyano, but I have no idea which molecule is that, right? But with rotational spectroscopy, you can know precisely which molecule is that. And that's the way we usually do it.
Thank you.
Good afternoon, sir. So my question is, in one of your slides, you just mentioned that borylene skeleton can be helped in activating the nitrogen molecule.
Yes.
So at present day, apart from the Haber's process, there is no such big industrial method of producing ammonia. Yeah. So that can that be used as a substitute of Haber chemistry in a greener way? I mean, in a greener approach.
That's our objective. Our objective is to use that. The main idea is that you are using an element which is abundant in the Earth's crust. Boron is relatively well abundant there. And you can do the reaction room temperature. The main problem with the Haber-Bosch process is that you have to elevate that to...
Yes, yes.
Yeah, I think it's 700 degrees Celsius or something like that. And only that reaction is associated with what? I think 2% of the entire energy consumption in the world is associated to a single reaction, which is that one.
Yeah.
So it's finding alternatives is something very important. This could be a way, but there's a lot of work in that direction yet. Because these borylenes, they only exist in glove boxes. If you expose them in air, they are so reactive that they react with everything. But, so you can say, so it's not going to work. But a few years back, that was the position of the carbines. So when they were synthesized, they saw, carbines are very interesting, but they're very reactive. You just open the flask and they react. Until in the 90s, someone discovered a carbine that is bottable. You can store that. And then this revolutionized several areas in industry and research. So perhaps the borylenes are the next carbines. We just need to find the appropriate structure to stabilize boron as a Lewis base. Because notice, boron is a Lewis acid. It's electron deficient. In borylenes, you are making boron a Lewis base. So it's fascinating chemistry.
Reverse.
You're just changing everything about boron when you have a borylene.
Thank you, sir.
Thank you.
Any more questions?
Thank you very much.
Okay. So we sincerely thank Professor Fantuzzi for a very illuminating and interesting lecture. But after that, I would just like to request our student Orithro, former student Orithro, to just say a few words about his experience and his research. Please.
Good afternoon, everyone. I think I am audible. First, my devotional pranam to Thakur Mashamiji and all the professors out here, and thanks to Philip for coming here. I'm not gonna give an academic talk, so it's like purely like how I met Felipe and our works. So my title is Networking, a Key Way to like boost your academic journey. And if you don't know me, I am Orithro Roy, a former student of Rkmvcc. I studied BSc from 2016 to 2019, and then I moved to Pondicherry University. So this is the chemistry department. Oh, sorry. I want to thank you directly. So this is the chemistry department at Pondicherry University, and there I was introduced with this whole computational chemistry thing, and then that's how I met Felipe. So he was the guy under whom I did my master's project on computational chemistry, not just only molecular level as well as materials level. I did work on borofin under Dr. M.M. Balakrishna Rajan, and after that I was looking for, at first I started planned for NET, didn't work. I didn't find, okay, it's very interesting for me to study for the whole thing, which I don't really like, because my plan was not to do a PhD, and I was only interested in computational chemistry. So I was thinking, okay, how can I get a PhD position without knowing everything in details, which is in the syllabus of NET, and that's going out from India. So I was looking for a position outside of India on my scope, and I was trying to also gain more experience on computational chemistry, experience with research experience. And by the time it was, I think, 2021 November, you joined Kent, right? So he joined as an assistant professor in Kent in 2021 November or December, and I think I basically tweeted him, like I followed him on Twitter, and he followed me back. I just sent a huge message, like this message on Twitter, like, okay, I want, so he advertised for his position under a vacant PhD position under his, because he joined as a new professor, so they give some funding from the university to get some PhD scholar. So I just messaged directly on Twitter, and this is the huge reply, like bigger than mine. Felipe sent it to me that, okay, these are the details how to apply and stuff, but we can talk. So we had a informal interview. For me it was formal, for him it was informal, but whatever. We had a talk in 1 week, I guess, and that's how we started discussing how can I get a PhD position outside, because my CV was not shortlisted by University of Kent, so I was looking for other positions because I can't stuck with just only one institute. And by this time I approached him, okay, can we do some work together, like a project? Can you involve me in a project so that I can get more experience and I can show that as a profile while applying outside? At first he was like, no, I can't pay you. That's the reason. I was like, no, I don't need money. I want some research experience to showcase and also gain some experience so that I can work better in future. And we started with this paper, like this project, where we used 3 aluminum in one those are in single bonds, so aluminum, 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 3 aluminum into single bonds. So usually they form like bent structure or they make rings, but in this case we found around 162 degree in experimental as almost a near aluminum structure, those tri-Allen structure. But we did the computational part and we found it is nearly 164 in computationally and experimentally 162, which was in collaboration with University of Würzburg, which is the postdoctoral institute from Felipe, and it was published in JAX. If you know, it's a very highly recognized journal from ACS. And then we did some more collaboration. These 2 are already published. One is in Sensors and Diagnostics by RSC and another in Elsevier. And these 2 papers are already submitted and we are planning to work in more. But definitely, we didn't just do work. So this is Felipe's house in UK. And this is Heidi. I don't think you can see, but yeah, this is his dog. His name is Bono, and there is cat. Okay, so this is the dog Bono, and this is the cat Nemo, and here I am. This is his wife Heidi. This is Felipe. So I went there, stayed, enjoyed, did some work. This is an like, I think it's a dinner, but at 6 in the evening. So for us, it's just a snack, but yeah, it's a dinner there with Nigel's group. So he is another professor from University of Kent, where with whom Philip does his work. It's in front of the chemistry department in University of Kent. This one is it's a like it's basically the moon, like when the USA launched, Neil Armstrong and others went to moon. So that's like the documentary on that. It's called Moonwalk. We went there together, and not importantly, Durga Puja is coming. So we celebrated Durga Puja on Ashtami in London. So this is Felipe, this is Heidi, here is me, my 2 friends, and these 2 are students of Felipe, and she is from here, like Barakpur. Now, I am not gonna going into details like how you can get PhD outside, but the way is like, I would say best 2 platform are LinkedIn and Twitter. You can search by hashtag, not just PhD position, you can even narrow down to your specific field. But there are other options like find a PhD, and if you are specific to computational chemistry or computational material science, AI for science, anything like that, then you are the best website is psyche.net. But yeah, these are the options you can look for, but there are other options also. But the most important thing is IELTS or TOEFL, whatever it is, the English speaking, not just English speaking, listening, reading and writing, all those you have to give if you want to do a PhD outside. This is the most important thing because it's gonna take at least 1 to 2 months if you are like concentrating well on specifically only to English, like that exam. And it costs like not a small amount. I think it's now 16 to 17,000 in Indian rupees, just the IELTS exam. When I gave it was 15,500. Last time I heard 1 year back it was 16,500. So it's increasing. You can give as many times as you want, but you have to pay that money. So be prepared and then give the exam. But this is very important if you want to go outside. I'm gonna finish here because this is days of Philip. I'm not gonna talk. I'm just going to thank my supervisors, because with Felipe I am doing just collaborations, but I am doing PhD under Dr. John Bakaridge, Chiara Gattinoni and Enrico Gisson. I am a PhD student at London South Bank University in UK, and these are the collaborators. Felipe is here. A special thanks to Felipe. That's all. Thank you. And if you want to contact me for anything, I think, yeah, here are all the details. This is my Indian WhatsApp number. Sorry, this is the WhatsApp number. You can just message me or send an email to here. Anything is welcome.
So thank you very much, Aritro. He has given his contact number, his mail ID as well. So if any one of you are interested in going abroad or getting any guidelines from him, you can directly contact him. So we sincerely thank Aritro and we wish him all the best for his future endeavors and wish him all the best for his collaboration with our respected Professor Felipe Fantuzzi. Now let me take this opportunity to thank all the organizers of this seminar. First of all, we must thank Professor Felipe Fantuzzi for coming to our institution and giving such a nice talk for our students, for us. It's a really illuminating talk and we enjoyed it thoroughly. So we thank him from core of our heart. We sincerely thank our revered Principal Maharaj, Swami Kamalasthanandaji, for giving us the opportunity to organize this seminar. We sincerely thank our departmental staff members for giving us the opportunity to arrange this seminar, our technical staff for this seminar hall and for these presentations and all that. And most importantly, we sincerely thank our students, without whom this seminar has got no meaning. So thank you all. Thank you. Now there's an announcement for the students. Students are requested to just sit back a little. First, let photo. Yes, মানে তাহলে এইখানে দাঁড়িয়ে তুলতে হবে, তাই না? কোথায় তুলবে? Do it. Go ahead. So we will have a photograph. Please just wait.